Hello everyone, my name is Kenneth. I'm from the School of Electrical and Electronic Engineering of Nanyang Technological University. And today I'd like to talk about a deep learning approach for modeling perceptual attributes of soundscapes. Now, perceptual attributes of soundscapes over here refers to factors such as the acoustic comfort, perceived loudness, or any measurement that can be done subjectively but quantitatively. We know that there has been this push to move away from decibel-based metrics based on the definition of soundscape because the decibel-based metrics fail to capture the acoustic environment in a holistic manner. As you all know, in part 1 of the International Standard for Soundscapes, the soundscape is defined as the acoustic environment as perceived, experienced, or understood by a people or person in context. Hence, we believe that models for such attributes should take into account the listener's perception as well as context, be that cultural or socio-economic or other similar factors. Here, I would like to draw a distinction between models for the analysis and models for the prediction of perceptual attributes. So analysis is where we collect data about both an independent and dependent variable, and then we try to draw relationships between the variables in a post hoc fashion. So this is after we have collected all the data. On the other hand, when we want to predict, we want a model that gives us an idea of what to expect about some dependent variable before we go out to measure it. And of course, that's given collected data about a separate independent variable. In this sense, analysis is more a post hoc extraction of features from the data, whereas prediction is more an a priori task to predict a value that has not been seen yet. So common analysis methods in the soundscape literature include principal components analysis, hierarchical cluster analysis, and self-organizing maps, among others. These are just some of the common ones. And for prediction models, we mainly have generalized regression models or multi-layer perceptrons. And just a side note, of course, there are techniques that can do both analysis and prediction, right? So for example, we could do principal components analysis, PCA, on some measured data and use the principal components in a regression model. However, it seems like deep learning has not yet taken off in soundscape research as a technique for building predictive models. This is despite recent advances in deep learning being relatively successfully applied to tasks related to the detection and classification of acoustic scenes and events. So originally, deep learning models were used for image classification, but many researchers have found that the same techniques were pretty much transferable wholesale into acoustic event classification, as well as a host of other acoustic tasks. Because we can always take as input some kind of short-time Fourier transform or spectrogram transform of an audio signal, and that would just be a 2D image representation of an audio signal. In fact, since soundscape studies are heavily dependent on the acoustic environment and acoustic stimuli around us, it is relatively conceivable for the same deep learning techniques to be applied in this context as well. Hence, for this project, we want to present a preliminary study of this, and specifically what we have done is to develop a model to predict the pleasantness and eventfulness of stimuli as rated by participants in our study. So how we went about doing this was firstly to conduct a laboratory experiment where we let participants listen to an acoustic stimulus here, and we got them to rate its pleasantness and eventfulness on 7-point scales over here. Then, to take into account the listener context, we also collected some basic demographic information here, as well as some responses regarding their attitudes and sensitivity towards noise here. These attitudes and sensitivity to noise questions were actually just statements that the participants rated on 5-point scales. And some examples of these statements are, I complain once I have run out of patience with the noise, and I am annoyed by even low noise levels. And so just a little point of clarification, we grouped the demographic information and attitude sensitivity to noise questions in the same questionnaire, which we called the listener context questionnaire over here. Then, with this data, we trained a deep neural network to predict what a given participant rated for the pleasantness and eventfulness on the right, given the acoustic stimulus, demographic information, and attitudes towards noise on the left here. Effectively, what we did here was to replace the participant with the neural network itself, as you can see from what I did on the slide. And the implication is that if we train the model well, if the model makes good predictions, then we don't even need the participants to physically listen to the stimuli anymore to get the pleasantness and eventfulness ratings on the right. And this would definitely save a lot of time for, say, urban planners who may need to test out certain soundscape designs across a variety of age groups, because now all you need to do is to input the raw audio data and the demographic information of any hypothetical person, right, or any responses to these questions hypothetically, and you don't even need to go out and find that person anymore. Then you can get an idea of what the expected pleasantness and eventfulness ratings would be. And in fact, with the current pandemic situation, it's probably not feasible to get many participants to come over, say, physically to the laboratory to make these subjective evaluations as well. So a good model could be convenient for research in that way. Specifically, for study here, actually, we used 100 acoustic stimuli, 100 recordings of bird songs which were each 30 seconds long. These recordings were taken from the Macaulay Library and a set of tracks from the Korean broadcasting system. And there were 127 participants in the study in total. So what we did was to combine them independently to form a threefold cross-validation set, as you can see in the diagram on the slide here. So for example, for the red-colored set, we had 36 participants here, listening each to 35 stimuli, which made 36 times 35, 1,260 data samples in total. And the participants and stimuli in the red, green, and blue sets, which we also call folds, were mutually exclusive from each other. This gave us 4,170 data samples in total to work with to train our model. And just a little note about the acoustic stimuli. The participants, of course, heard the raw audio through a pair of headphones. But when we fed the acoustic stimuli to the model to train it, we converted them into Mel spectrograms first. A Mel spectrogram is just an STFT, a short-time Fourier transform, transformed with a Mel scale filter bank. And this is just a scale of pitches judged by listeners to be equal in distance from each other. So in this slide, you can see a time domain plot of one of the stimuli we used for the study, and its corresponding Mel spectrogram below, plotted as a heat map. As for the listener context questionnaire, however, we just encoded the participants' responses as a 13-dimensional real-valued vector before feeding it into the model. With these inputs, let me give you an overview of the model architecture that we used. And essentially, we have a listener context branch on the left here, and a spectrogram branch on the right here, which are eventually combined at the end over here to make the final predictions. So the listener context branch is where we fed the 13-dimensional vectors into, and is primarily made of a dense layer with a rectified linear activation function. That's the ReLU function over here. So it effectively performs much like a multi-layer perceptron. On the other hand, the spectrogram branch is where we fed the spectrograms into. So 64 by 2, 582 by 1 here is just the dimension of each spectrogram. And this is primarily a convolutional neural network with 5 blocks here of convolutional layers and activation functions, which are highlighted in blue. The listener context branch and spectrogram branch will output certain trained features that are concatenated over here at the output of both branches and sent through 2 more dense layers before outputting 2 values, the predicted pleasantness and eventfulness as rated by the participant. That's why the output is 2 by 1, because the values correspond to the pleasantness and eventfulness. To sum up, what we have here in this deep network architecture is actually just a relatively sophisticated nonlinear regression model, because as I mentioned previously, the output is just going to be a number each for the pleasantness and eventfulness. To train this model, we used the threefold cross-validation set that I mentioned earlier, and I put the diagram back here for your reference. The way we used it specifically was to use each fold in turn as test data, and then use the other 2 folds to train the model. This way we can get an unbiased evaluation of the model performance. So for example, if we used the samples in the red and green folds over here to train the model, then we would use the samples in the blue fold here to test the model. The entire training process was actually done on TensorFlow, and we used an Adam optimizer to optimize the weights of the model with L2 regularization applied to all the weights of the model as well. The learning rate and regularization constant were the same, 0.001. And as the result, we got these results which I summarized in the table on this slide. This table shows the model performance, essentially the mean absolute error and mean squared error when making the predictions for both pleasantness and eventfulness on each of the three folds, the red, green, and blue folds, which I've labeled here also as folds 1, 2, and 3. Of course, we got the participants to rate the pleasantness and eventfulness on 7-point scales as well, so all the errors here are with respect to that 7-point scale. Firstly, we can see that the model performs comparably for both the pleasantness and eventfulness. The mean absolute error for both attributes was about 1, meaning that the predictions were plus or minus 1 away from what each participant rated. However, we also happened to have a relatively small data set in the context of deep learning. In particular, because of the way we split the cross-validation set, the model only had either 2,520 or 2,910 samples to learn from, where the first number, 2,520, is for fold 3, and 2,910 is for folds 1 and 2. And we trained the model from scratch, so the amount of training data might not have been completely suitable for the depth of the model that we used. Of course, there are also pre-trained model and feature extractors out there like VGG-ish or OpenL3 that we can potentially use in the future to deal with this issue of having a small data set. Lastly, we can also see from this table that the model performed slightly worse in fold 3 here as compared to folds 1 and 2. And again, this is likely to be a result of the difference in training set size between the three folds, because the model only had 2,520 samples for fold 3, and as compared to 2,910 training samples for folds 1 and 2. So in fact, if we compare the data and the performance between fold 3 and folds 1 and 2, we can see that actually with the increase in the number of training samples by about 400, the model performance improved by about 0.1 in terms of mean absolute error. So actually, it seems like at the scale of the data that we have now, increasing the number of samples available to the model does indeed improve its performance significantly. And I would just like to conclude my presentation by providing some insights into what we have done and what we can do to build on it in the future. For this presentation, we looked at a method using deep learning to develop a model that can be used to predict subjective ratings of pleasantness and eventfulness given some training data. Of course, we're not limited to only pleasantness and eventfulness in applying the techniques that I described in this video. We can use the same techniques, even the same architecture, to predict acoustic comfort or perceived loudness or any other subjective metric that you might want to measure. And in this manner, I hope that I have shown the applicability of deep learning techniques to soundscape research. As for future work, one thing we could do is to expand the complexity and quantity of acoustic stimuli in the experiments, because the present study only used bird songs as acoustic stimuli. So to expand this complexity, we could add on acoustic stimuli from real-life recordings or combine together multiple sources. And as I mentioned in the previous slide, we could also use pre-trained models instead of training the model from scratch. That's the VGG-ish and OpenL3 models that I talked about. And with that, I would like to end my presentation, and thank you very much for listening to me.